Yeah, so I'd like to get started. So welcome to the UTIG seminar. I'm very pleased to introduce today's seminar speaker, Eli Tziperman. So Eli is a professor of oceanography and applied physics at Harvard University. And he received bachelor's degree in physics and math from Harvard University in Israel in 1982. And then he received a PhD degree in physical oceanography from the MIT Woods Hole Joint Program in 1987. And he then moved to the Weizmann Institute of Science in Israel as a postdoc, and then was eventually promoted to a full professor there in 1998. And Eli returned to the US in 2003 and became a professor at Harvard University. So I've known Eli's name for many years because he has done one of the classic studies of ENSO, El Nino Southern Oscillation variability, which is my areas of research. But Eli's ENSO work is only a small portion of a very broad array of research. So his research interest is impressively broad, including like some helium circulation, abrupt climate changes, warm climates, and glacial cycles, and snowball Earth, ocean data simulation, and even Europe as ocean dynamics. So today, he's going to tell us about his research on warm climate surprises. And he has two parts in his talk. And the first one is enhanced frequency of sudden stratospheric warming events. And then part two will be a future for California. So I'll stop here and please start the presentation. Thank you.
Hi, everyone, and glad to be here. I was wondering, given that we're such a small and intimate group, would it make sense for everyone to move to the front row so I can
I'm the only one that ever does that.
No, not today, not today. Would that be okay? Great, thank you. Amazing, thanks. What's your name?
Jamie Austin. I was a joint program graduate too.
Nice to meet you.
Nice to
Jamie,
meet you.
you're welcome to move one forward if
then,
you're.
you know, then I blot the screen out. And then
Very good. Just wanted to make sure that it would be okay. And I understand that, thank you, this makes such a big difference, admittedly. I understand that it's a very broad audience, right? Do we have geophysics people or? Okay, great. So I'm going to try and keep this general audience. If I don't, please yell at me and I'll try to do my best. That's the plan. So I'm assuming that you don't know what sudden stratospheric warming events are. So I'll try to tell you what they are, why they're important, and then why we think they might become more frequent in the future. In part two, I'll tell you that even though all of the projections for California in the future in a warmer climate are that it will be drier, we think that might actually be wrong and it might actually be wetter. And I'll try to explain why and propose a mechanism for that. This is the work of two of my students, as I'll mention now. So jumping to part one. So this is the work of Wanying Kang. She's now an assistant professor at MIT, a very brilliant woman. And so first of all, what are sudden stratospheric warming events? So here's an example. It's an animation of the polar vortex high above the Arctic. So what we're looking at is sort of looking at the North Pole from above. And this is the polar vortex. It's huge. It's thousands of kilometers big. We're looking at 2012. And this is an observed event. So you can see the vortex started as a big coherent thing, but then it's sort of breaking down, becoming small. And within just a few weeks, and now instead of having one eddy, we have three different vortices. So a very, very dramatic event. The temperature in the Arctic stratosphere increases by 40 degrees Celsius when that happens within just a couple of weeks. Any questions about sudden stratospheric warming so far? Okay, great. So let's see some more about that. Another animation, this time again, observations 2018. This is called the split event. You see the vortex changing, you see the vertical dimension here, and then it becomes two vortices. So that's called a split event. So we could have a collapse event, a split event, or a display event where the polar vortex just moves from the pole to somewhere else. These are all things that happen roughly 6 times per decade in the present climate. Why do we care? We'll get into the why do we care. So this just shows in red, it's the temperature. So you see when, let's start with the blue one. It shows the polar night jet. So the magnitude of this eddy becoming strong every winter. This is a seasonal thing. And then sometimes you have an event like this right here. So the vortex collapses completely and the magnitude of the circulation goes and becomes negative. And when that happens, you see the temperature increasing by 40 degrees, as I mentioned before. And you can see the normal situation right here. And these are the displacement and split events. And I think we covered this. So what do we know about this in the future? So there's a total disagreement about this. Some models predict that there would be more frequent events. Here are some references. Some predict that there's going to be less. The results are not conclusive, and there's no clear mechanism proposed for why the frequency of these events or their magnitude might change in the future, and that's what we're trying to do here. Any questions now about sudden stratospheric warming events? Thank you. Today, it used to be balloons, but today you could do it from satellites. Yeah. So in the satellite period, this became easier, obviously. Okay. Why do we care? Why do we care about something that happens 20 to 50 kilometers above the surface? So this shows why we care. There is a claim. So what do we see here? This is time. And this is height going all the way from tens of kilometers in the atmosphere to the surface. These are pressure coordinates. And you can see something starting here in the upper stratosphere. This red indicates that the polar vortex is doing something. I'm not getting into the details. And then you see the signal propagating to the surface. And the claim is that when the polar vortex breaks down, as we saw in these animations, the winter temperatures in either Chicago, for example, or Berlin or Paris could become very, very cold. So sometimes you get an event like this and the temperature in Berlin would be colder than it is at the North Pole. So extreme cold temperature events during the winter seem to be, and I'm saying seem to be because it's being debated, but seem to be related to these polar stratospheric vortex collapse events. So that's why we care about these events. And again, today they happen 6 times per decade.
The average weatherman is using the term polar vortex now.
This is the polar vortex, yeah. Right. The only thing to be careful is that there's a jet in the troposphere, in the lower troposphere, and there's a jet in the stratosphere. We're talking about the one in the upper atmosphere, in the stratosphere. But yeah, they often talk about it in these terms that you mentioned. Okay, I think we said everything there is to be said about this. This was our hero number 1. Hero number 2 in this story is something called the Madden-Julian Oscillation. Madden-Julian Oscillation is something that doesn't happen in the stratosphere. It happens in the troposphere, in the lower part of the atmosphere. This is an animation of that. So what you see in the Madden-Julian Oscillation is clouds and precipitation form over the Indian Ocean and then slowly propagate at the speed of about 5 meters per second into the West Pacific, and then they disappear there. The time scale, if you sit in one place, is roughly 40 days. And this thing happens continuously during the right season. So this is our second hero, again, the Madden-Julian Oscillation. This was discovered in the 70s by Madden and Julian, obviously. The mechanism of the Madden-Julian Oscillation is still being debated by tropical meteorologists. So it's a very smart group of people and they still didn't figure it out completely. This provides a source of living for them for many, many years. Okay. And I should say that this affects the weather all around the Pacific. And this is the dominant weather event in the Pacific. If you discount El Nino and the seasonal cycle, this is the next important thing, I believe. Okay. So it's a very dramatic thing that happens regularly and has a 40-day scale, and it happens in the lower atmosphere and the troposphere. Okay. So now I'm getting into our story. So my story is about the interaction between this Madden-Julian oscillation and the sudden stratospheric warming in a warmer climate. So what is our motivation for getting into this? It has been observed. This is something that has to do with the MJO, and this is something that has to do with the polar vortex. And the colors here basically indicate that when the MJO changes, the polar stratosphere changes as well. This doesn't reflect anything that happens to the polar vortex necessarily. It just shows that there's some correlation between the MJO in the tropics and the polar cap in the stratosphere. So that's one point that we noticed. And then the second thing, we did some work and many others did as well. These colors indicate the magnitude of the Madden-Julian oscillation at 1 times CO2 and 4 times CO2. And what this shows you is that the magnitude in a warm climate gets much stronger. You see the colors here are getting stronger and it extends more to the right, which means it propagates more into the Pacific. So the MJO gets stronger. We predict that the MJO gets stronger in a warmer climate. We think there's a good understanding for why that happens. So that seems to be a fairly robust thing. And there's already a connection between the MJO and the stratosphere. So one wonders, if the MJO gets stronger, will that mean that even sudden stratospheric warming events can change? So that's the question we're raising here. Is it possible that the strengthening of this tropical Madden-Julian oscillation in the warmer climate would lead to more of an effect on the Arctic stratosphere and more sudden stratospheric warming events? So that's the question we're asking, and I'll try to tell you what the answer is. The answer is, we think so. We think the number of sudden stratospheric warming events might increase dramatically because of the strengthening of the Madden-Julian oscillation. Any questions so far? Yes.
So what's the interaction between the MJO
And that's what I'm going to describe. It's basically the MJO is emitting waves, and these waves make it all the way to the stratosphere. That's one, and there's another one. There will be more events according to this story that I'm about to tell. Twice as many in the particular simulations that we did. Okay, nice. Thank you for asking questions, obviously. Okay, so one slide with all of the main results here. So we've used all sorts of models. There's idealized atmospheric models and realistic atmospheric models. So throughout, you'll see results from both idealized and realistic. The blue line is some index that represents the sudden stratospheric warming, or the amplitude of the polar vortex in the stratosphere. And every time the blue index crosses the 0 line, there's an event. It's called the major sudden stratospheric warming event. And the red one is a simulation with a stronger MJO. And the number of events doubled. So that result number one is because of the strengthening of the Madden-Julian oscillation, there are twice as many sudden stratospheric warming events. And the mechanism, just briefly before I get into details, there are two mechanisms. One, so what is this curve? So we have the troposphere and stratosphere. So this is the vertical axis in the atmosphere. Surface is here, top of the atmosphere is there. And this is latitude going from the equator to the North Pole. So the MJO happens in the tropics, in the lower atmosphere, and the polar night jet, the sudden stratospheric vortex, happens in the stratosphere in the Arctic. So the way the MJO affects this, according to what we are finding, and I'll show you, is the MJO emits waves, and when it's stronger, it emits more waves that propagate all the way to the stratosphere and affect the polar night jet. That's one mechanism. The second mechanism seems to be even more dominant. The MJO emits these waves. It affects the tropospheric jet, the subtropical tropospheric jet, and that creates something called stationary waves that again propagates to the stratosphere and affect the polar vortex. So the MJO acts both directly and indirectly to affect the stratosphere, and that's how it enhances the frequency by a factor of 2. That's sort of the overview. I'll show you some details now. Any questions about the overview? Yeah, I'll show you. That's a very good question. I'll show you the phases. There are some preferred phases of the MJO in which the waves do manage to make it. Yeah, that's a very good question. You'll see on one of the next slides. Anything else about this overview? Something called Rossby waves. So these are what we call planetary waves. These are waves that depend on the beta effect, the change in the Coriolis force with latitude. The weather events can be thought about as Rossby waves. These Rossby waves propagate both horizontally and vertically, and they're excited by the MJO, which is very large scale. So, yes.
Does this mean that other tropospheric events at similar latitudes but in different parts of the globe could also cause a polar night jet?
This mechanism is very particular, as I'll show you in a second. So it's not that easy to do it with anything that happens in the tropic. The MJO has some very specific properties that actually are able to do this, and I'll demonstrate that hopefully. Okay, thanks again for the questions. Wonderful. Okay, so we use two tools. One is a realistic GCM and one is an idealized GCM. This is technical. I'm skipping this. Okay, so first we increase the magnitude. I don't suppose there's a stick here, a pointer. Okay, never mind. So we increase the amplitude of the MJO, and this is the result. This is the result. So this is the temperature, and this is the zonal velocity. And you see the temperature is function of latitude and height, and you see the red patch there indicates that the temperature, when we increase the amplitude of this Madden-Julian oscillation in the model, and we prescribe it to be stronger, artificially kind of, because we know it's going to be stronger in the future based on other studies, then you see the red patch indicates that the stratosphere is getting warmer, and that's mostly because there's twice as many sudden stratospheric warming events during which the temperature increases by 40 degrees, and U is the strength of the polar vortex is decreasing. That's the blue patch in the right top corner there in the stratosphere. And I showed you that one. So instead of having 30 sudden stratospheric warming events in a period of 50 years in this simulation, you get roughly 60. So the frequency it becomes twice as much. So if today it happens 6 times per decade, 6 times per decade, it would happen twice as many if you believe this. This is a very idealized model, but we also did it with a realistic model of the stratosphere, and basically one gets the same result. So this one has 10 events in the normal run, and it jumps to 21. And you can see the difference between the two is mostly that this model actually has a seasonal cycle. So the jet increases and decreases. And when a sudden stratospheric warming event happens, so here's an example, you see the blue thing here. So the jet develops during the winter, and then suddenly in the middle, it dips all the way, becomes negative. So that's a very important, that's a very strong collapse of the polar vortex, a sudden stratospheric warming events, and then it recovers and the seasonal cycle continues. So these events double in their frequency as a result. So the question is, why does this happen?
Can I ask a really provocative right now question? Why would anybody living on the surface of the planet care? I mean, you get 10 as opposed to 21.
Right.
It translates to what?
Yeah, this has to do with this thing that I mentioned before. So when something happens in the stratosphere, this is the upper atmosphere right here, and this is the surface. Eventually, it propagates downward and affects and creates these extreme weather events at the surface.
So it's extreme weather of all kinds, more precipitation.
I think
more
it's mostly
storms.
cold. I think it's mostly cold events in the winter. There was one in Chicago, not recently. There's one in Europe from time to time. That's how it's mostly manifested. That's a very important question, obviously. Okay. So we see a doubling of the frequency, and we want to know why. Okay, I'm looking at the clock. This shows that this is some diagnostic. So it's Hertel PV for those who are interested in the fluid dynamics. It's a Hertel potential vorticity shown as function of both latitude and MJO phase, and also height in pressure and MJO phase. And the third one shows a momentum flux. Basically, all of these are saying something very simple. During phases 4, 5 of the MJO, that was in response to your question, these waves that are emitted by the Madden-Julian oscillation manage to make it to the polar vortex and disrupt it. So these are model diagnostics that show the propagation of the waves. And this is in the horizontal plane. If you look at the upper panels, you see different phases of the Madden-Julian oscillation, and the color patches indicate propagation in latitude of these perturbations that are excited by the Madden-Julian oscillation and how they make it to the polar vortex. So you can see that it's complicated. The waves have to travel in latitude, in height, and in longitude, but eventually they make it to the polar stratosphere and make a difference there. Nice.
So it's phase 5 of MJO is when the convection moves over to the Western Pacific.
Yeah, the forcing needs to happen. You'll see in a second that the fact that MJO happens in the Western Pacific is critical. So yeah. What exactly about which phase of the MJO does this is not completely obvious to me. So I can't really answer that question too well, admittedly. Okay. I'm thinking for us, maybe this is unnecessarily technical, so never mind. So then there's the jet, right? So this is what the jet looks like normally. So what's plotted here? So you recognize, let's see, the Indian Ocean here, just below this area in the Pacific, latitude. And the red patch is the zonal velocity. So this is the eastward atmospheric velocity due to the subtropical atmospheric jet, which is at a height of say 5, 6, 7 kilometers, something like that, okay? So it's a tropospheric jet. It's not the jet in the stratosphere, it's a tropospheric jet. And that's what it looks like when there's no MJO forcing. So now I'm going to show you what happens to this when we introduce MJO forcing, and you'll see why the interaction with the jet makes a difference. So is it clear what this is? You can see a large eastward velocity. You know, it's not going straight. It's obviously tilted in the Pacific. It's related to the storm track. I mean, it's not this. Yeah, never mind. So now when you introduce the MJO forcing, you can compare this panel to that panel, and you see that this one has become much less zonally symmetric. Here, the color red is spread over many longitudes, but here the red color is actually limited to some longitudes. So it became more restricted in longitude. When you put, so this is what for the realistic location of the MJO forcing. If instead you put the MJO forcing at a different longitude, the jet actually becomes weaker and even more zonally spread. So the fact that the MJO works acts in the Indian and West Pacific allows it to change the jet in a way that makes the jet less zonally symmetric. So it's more restricted in longitude. And that means that it emits more what's known as stationary Rossby waves. These stationary Rossby waves then make it to the stratosphere and affect the polar vortex. That's what we find basically. Okay, so the B here is the area of the MJO forcing. If we put stronger forcing here due to the MJO, this will make the jet less symmetric in longitude, so more limited. This means more of these stationary waves, and this causes the disruptions. So the interaction between the MJO and the jet is a critical part of that, and it's a bit complicated, but I think it's not that difficult to understand this from these pictures. Any questions about this?
With waves, like we have like two model. I think it's kind of like it's not just one unit, but it's going to be divided into 2 or 3. So it's like waves.
So there are two types of waves in this picture. One type of waves is the waves emitted by the Madden-Julian oscillation. So the Madden-Julian has a time scale of 40 days, roughly 40 days, say 20 to 100. So these are going to be time-dependent waves. These time-dependent waves make this change to the jet. And then the jet has a longer time scale in this picture. And because it's almost stationary, this would lead to waves that have frequency 0. These frequency 0 waves can propagate to the stratosphere. The wavelength of these waves is also always wave number 1 and 2. So this means that there's just 1 or 2 waves going across the globe. So these are very long waves in the east-west direction that manage, and such long waves are known to be able to penetrate into the stratosphere. Does that make sense? Yes. I mentioned several phases. There's the MJO phase. So the MJO has been divided into 8 stages, and they're referred to as phases 1 to 8. And people typically ask at what phase of the MJO this happens. So that's what we tried to discuss before. Not that critical, admittedly. Nice. Okay, to conclude part 1. So I tried to suggest that if we have a stronger Madden-Julian oscillation in the tropics, so in the lower atmosphere, in the tropics, in the troposphere, which might happen in a warmer climate, there are strong indications that might be the case. This might lead to more frequent sudden stratospheric warmings and therefore maybe more extreme events if you want. And we talked about the mechanism, and the mechanism had to do with both directly forced waves that propagate from the MJO to the stratosphere, and also with this effect of the MJO affecting the jet and the jet affecting the polar vortex. Technical. Now, the difficulty in studying this is you need a model that can simulate the MJO and sudden stratospheric warmings at the same time. Such a model didn't exist when we did this study like 4 years ago. Then we tried to develop one in collaboration with Dave Randall, with something called super parameterized atmospheric GCM that has a stratosphere. Ended up a very complicated picture, but today there is such a model that was actually developed in NCAR, National Center for Atmospheric Research, and we're now using it to study whether this would be the case. So in that model, in all of this study, we just imposed a strong MJO. In that study, we're just going to increase the CO2, see that the MJO strengthens, and see whether this would lead to more frequent events. So this will finally be able to disprove everything that we've done, and we can throw away the papers that we wrote about this. That's the plan. Yes.
What's the mechanism predicted for the warming climate of higher CO2 to generate stronger MJO?
That's a talk on its own, but the one sentence version of that is that in a warmer climate, you expect the vertical profile of moist static energy to become steeper, and this leads to a stronger Madden-Julian oscillation. That's the one sentence summary of that one. If you come later, I'm happy to show you more. Yes.
One of our research.
Ita asks, has there been work done on the potential behavior of the MJO during different paleoclimate regimes? Could the climate state dependence of the MJO be an unrecognized confounding factor for interpreting polar proxy records?
Yeah, there has been work by Matt Huber and others in which they simply ran simulations and showed that in a warmer climate, the MJO gets stronger. There are many studies like that for the future climate, and some studies like that that we're trying to be relevant to past warm climates, such as the climate of, say, 2 to 5 million years ago, or to the climate of 50 million years ago, which was even warmer.
So I wrap my head around
Eric.
Why the MJO changes in amplitude affect frequency in terms of the physics word,
Right.
instead of, and the amplitude stayed the same. It's 40 degrees
Nice.
all the time, this SSW,
Let me
correct?
try. Excellent. And if you think about these collapses, the polar vortex has a certain velocity. When a sudden stratospheric warming event happens, by definition, the vortex collapses to 0. So it can get worse than that. So that's why the amplitude is not likely to change. But if you think about these collapses as being forced by noise that's being propagated from below, and which is the mechanism that we've understood since the 70s of the previous century, then more noise from below, which is what the MJO does, will excite more such collapses. So that's why we think the frequency might change, and you worry less about the magnitude. The magnitude is maximized by the fact the vortex already collapses when these happen.
So it's a simultaneous kind of process, or there is a time lag between the MJO and the effect?
There's a 2 to 3 weeks delay between the MJO and the effects on the stratosphere because of the wave propagation there. That's what we find. Nice. Okay. Great, that was part one. Something completely different now. Okay, so a wet future for California, where the work of Min Fu with these collaborators, Mark and Peter Molnar, who actually just passed away. These are papers just came out in the last year or so. So I'm going to show you some more evidence of this, but the Southwest US in particular is projected to be drier in a future warmer climate. That's a very robust prediction of many climate models. Last time the CO2 was high, 400 ppm, as it is now and so on, was the Pliocene 2 to 5 million years ago. At that time, interestingly enough, California was significantly wetter. So there's a contradiction. In the past, when last time there was a warm climate like we're expecting in the future, California was wet, but the projections are that California will be dry. So there's a problem, obviously. We're trying to resolve that problem. So we're proposing a feedback that might have been responsible for California or the Southwest US being wetter at the time. And we explain why that feedback cannot be represented by state-of-the-art climate models. Make sense? Okay, so let's go through this slowly. So first of all, California drought. So this is, which lake is this? The Folsom Lake. So you can see these lines here are basically the previous shores of this line. So the water has been retreating significantly. This is some drought area in California. The governor of California signing some things limiting water consumption and so on. So in the news, you hear about California droughts all the time. In fact, there's this study. So what do we see here? This is a time series of PDSI. PDSI is the Palmer Drought Severity Index. It's an index of how strong a drought is. It's been reconstructed from tree rings for the last 1,000 years or so. And then there's the event of the recent past. And the claim in this paper mentioned here is that the last severe drought is the most severe in 1,200 years. I mean, there are many limits to such a study because these tree rings are very uncertain, but you know, it's a suggestion that people have. So that's about how severe the droughts are right now, according to this. And if you look at future projections, so these are two different models and the projection for soil moisture, and you can see soil moisture dropping dramatically in this model in particular, and also in the GFDL model. So the projection is that California, the Southwest, will get significantly drier in a future warmer climate. And the claim is that we're already seeing it now in the record. Questions so far?
The last slide, there's some periodicity of the ground, and it will come back.
You mean this?
The bottom figure.
This one is so noisy that it's really difficult to tell, right? Again, it's from tree rings. If you actually, this record is the average of hundreds of trees. If you look at individual trees, they're all over the place. So it's really difficult to get a certain answer from tree rings, but if you average over enough of them, the claim is that this gives a fairly robust climate signal. So at least you know the baseline and you can compare it to what's happening recently, and you can suggest that maybe what's happening recently is perhaps especially severe. That's the idea here. Okay. So these are the future projections. So this is the CO2. Now the Pliocene. So these are so the CO2 right now is 400 and something, and projections depend on which scenario, suggest all the way to maybe 900 parts per million in a business as usual scenario by the end of the century. The Pliocene from 2 to 5 million years ago had the CO2. So you see, this is the line of 400. So you see as you go back in time, this is the present 1, 2, 3, 4, 5 million years ago, you can see that the estimates are roughly as high as 400 parts per million. Now, CO2 reconstruction is well known for being very, very uncertain. So I wouldn't trust that too much, but basically it says that the CO2 wasn't huge at that time. Maybe it was 400. That seems to be the common wisdom. You can take that with a grain of salt, but I think it's fair. So what happened during the Pliocene when it was 400 ppm? So just to put things in perspective, this is the climate of the last 60 million years ago. So you see that 50 million years ago, this is deep ocean temperature. The temperature was maximal. This is referred to as the Eocene. Climate has been, so at that time, there was no ice anywhere on Earth. There was no ice in Antarctica, no ice in Greenland, and so on. And then climate has been cooling for the last 50 million years. And between 3 and 5, climate was still warmer than today, but that's just before ice ages began in the Northern Hemisphere. And this is the period we're thinking about right here, the Pliocene, 2 to 5 million years ago. Questions about this one? Okay, how do we know about the Pliocene and what do we know? So we think the CO2 was in this range, 350 to 500, which is roughly the same as today already. The global average temperature was about 3 degrees warmer than today. These are the estimates. Ice was over Antarctica, less so in the Northern Hemisphere. And this is how we know. People go and dig these deep sea cores, and then they analyze the biological material from the bottom, both foraminifera and others, and they look at magnesium-calcium ratios, for example, in other proxies. And so these chemical or isotopic indications from the skeleton of plankton that grew at that time that are found at the bottom give you an idea of what the temperature was at that time. So what do we know about the temperature? We see this interesting result. So the temperature, so the picture is of the present day sea surface temperature. The numbers indicate how much warmer was it during the Pliocene. So this area of California was like 9 degrees warmer, 9 degrees Celsius warmer. That's huge. This area was also warmer, and so this is the Benguela area. This is the Humboldt, and this is the Canary Islands. So these four areas, this one, and this one are areas where we have upwelling today, coastal upwelling. I'll show more about that. So these are very special areas in today's world, and we'll talk more about that in a second. But basically, remember the average warming at that time was 3 degrees, but these areas warmed up to 9 or 10 degrees. So something very dramatic happened regionally in these areas, including close to California. These are upwelling areas today. You can see the surface temperature. So these blues indicate that the water is significantly colder close to the coast because of the upwelling, the rising of deep water that is very cold from below. Okay, this is what this southwest of the US looked like in the Pliocene 2 to 5 million years ago. So you see lakes. Death Valley had a lake. Other areas had lakes. Very, very different picture from today and from the projections of a dry California. So that's the mystery here. How could that be? And what are we missing in our projections? Or maybe we're not missing what's going on. This is how we know that sort of thing. So you go to these desert areas today, and you find signs of plankton that typically lives in freshwater lakes, for example, or this creature right here, the ostracod, or you can see these layers that are deposited in lakes. And that's how you know that what is a desert today was a lake. And people even reconstruct the lake boundaries. And these were pretty large lakes that sustained for millions of years during that warm period of the Pliocene. Any questions about this? All right. Okay. So our mechanism is going to be some interaction of this cold water that's coming from below and the wetness of California and so on. So I need to start introducing elements that will explain the mechanism that we're proposing for why California might have been wet in the past. So the first player is this upwelling. So you probably know this when the wind blows, say in the Northern Hemisphere, southward, along the coastline, there's going to be a motion to the right of that, and the water that's moving off the coast close to the surface because of the wind and the Coriolis force needs to be replaced with water coming from below, and that leads to this upwelling. So if you weaken the winds, for example, this would weaken the upwelling. Okay, so this has to do with the Coriolis force and so on. Okay, so here's the feedback we're proposing. So it's going to be a full loop. So we're saying the following thing. We're proposing the following thing. If the land is wetter, then we're claiming this would weaken these winds that drive the upwelling. And I'll explain why. Okay, that's the first step of the feedback. Wet land leads to weaker alongshore winds. Next step is that this would weaken the upwelling, obviously, because the upwelling is driven by the winds. The next step is that because the upwelling becomes weaker, this warms the SST. So remember, we have an evidence that the land was wetter because there were lakes, and we have evidence that the SST was warmer. So these two are supported by observations from the Pliocene. And finally, we'll show that if the SST is warmer, this makes the land warmer. So this is a positive feedback. So when it's triggered at some point, maybe at high CO2, this will reinforce itself and make the land wetter and wetter, and the SST warmer and warmer, and the upwelling weaker and weaker. That's the story I'm about to tell you. Any questions about this feedback loop?
So I understand the left two arrows and then right bottom arrows, but how does the wetter land lead to?
I will explain that
wetter-
now, yeah.
Okay.
Great.
Thank you.
Okay. Now, given the time, I'll do this briefly. What we're doing is this. In order to show that wetter land changes these winds, so we take this atmospheric model and prescribe these areas that are highlighted in blue to be wetter. We just prescribe artificially this area to be wetter by changing the land type in the model to a wetland. It could be 50% wetland, 70% wetland, 20% wetland, but it's basically being prescribed, and then we see what the effect is on the winds. So what do we find? In the California area specifically, this is the result. This particular panel here shows the results of making California wetter, and you can see the wind vectors blow from south to north in the opposite direction to the actual winds that go in this direction. So this means that this is the anomaly forced by the wetter land. So this means that when we make this area wetter, the winds that are typically blowing that way become weaker because the anomaly is in the opposite direction. So this shows that indeed the wind along the coast is getting weaker. That will make the upwelling weaker. Why does this happen? You can think about it in the following way. So if you had no continents, there would be a low pressure at the equator, a high pressure at 30 north. Because of the continents, you break this continuous stripe of high pressure with the land. Then when you have a high pressure and the land is something else, the high pressure introduces a circulation, a wind circulation, like this. And this creates these winds. Okay, so the winds that are upwelling favorable, the winds that are forcing the upwelling are a result of one, the Hadley cell that creates a high pressure here, and two, the presence of land. So now if you have a wetland, this effectively moves the boundary between land and ocean to the right, to the east. And that means that these winds, instead of blowing along the coast, will either get weaker or move inland. And that's why the winds weaken above the upwelling region. That's sort of the short explanation. Does that make sense? Okay, great. Okay, so now we explained roughly why is it that when there's a wetland, the winds will weaken. When the winds weaken, the SST will warm, and when the SST is warm, we're claiming that the land would be wetter. So what is the mechanism for that? So for that, we do a different set of experiments in which we prescribe a warm SST signal. So this is the perturbation we're prescribing. And we watch the response of precipitation over land. So this would be the anomaly for the sea surface temperature that would be imposed, that would be a result of a weakening upwelling. Okay. And we want to see what is the result for the precipitation over land. And we see that in fact, this red here indicates that the precipitation increases as a result of this SST perturbation. Why does it increase? So, especially in summer, why does it increase? Because there are more cyclones arriving to the area in winter, and there's more convection during summer. Anyway, so this is the mechanism. If I'm happy to tell you more later, but I want to leave time for questions at the end. So basically, we understand why when you perturb this, when you warm the sea surface temperature here, you get more precipitation. There are more storms coming here, and also the air is more, the atmosphere is more unstable to precipitation. And this varies between summer and winter, but in both cases, you get more precipitation. So that completes the loop in this area of why is it that the warmer sea surface temperature leads to a wetter land. Okay, so let me just summarize this. So future projections are the California Southwest will be dry. The past shows that it was actually much, much wetter than today. And we're proposing this feedback. So let me remind you what the feedback said. It was saying if the land is wetter, this weakens the winds. We talked about why. If the winds are weaker, the upwelling becomes weaker. If the upwelling is weaker, the sea surface temperature is warming because less cold water is coming from below. So the surface will warm. And we show that if the SST is warm, this leads to a wetter land. So this feedback can lead to more and more wettening of California. When this will be triggered and how, maybe at a high CO2, we don't exactly know when this will be triggered. That would be an interesting question by itself. And this is an important point. This feedback can't be simulated by current climate models. Let me explain why. Two reasons. One, because the resolution of the ocean models that are used in these climate models doesn't allow them to properly simulate this upwelling system. The width of the upwelling system is maybe 20 kilometers, but the resolution of these models is 50. It should have been 2 kilometers to simulate a 20-kilometer wide area. So they can't simulate the upwelling correctly. And maybe that's why they're missing this. And the second reason is that the atmospheric model needs to be able to change the land type with climate. So, you know, if the model, the land type is typically specified, say shrubland or wetland or something, but these models typically cannot change the type of land on their own during the model run. That's something that still isn't part of these models. And these are these two things. And that's why the feedback can't be simulated by these current climate models. So it's at least possible that the projections that California will dry are wrong, at least in the long term, say 2100 in a business as usual scenario. Imagine that maybe such a feedback can be triggered and change the picture dramatically from the one that's currently projected. This isn't necessarily good news, by the way, because if the upwelling stops, then these small upwelling regions account for 25% of the fisheries today. So we'll get a wet California, but we won't have fisheries. So you could grow stuff on land, but you're going to lose your fish or whichever. So I'm not telling you this is good news in no way. So basically, I think the bottom line here is just that the uncertainty in future projections of a dry California is higher than we think. So I wouldn't treat what we're saying as a projection. I would just say this is an attempt to constrain the uncertainty, and we're claiming that the uncertainty is actually larger than you would think, based on the fact that all models predict the Southwest to get drier. Yes. Okay.
Thank you. Okay, so Gita asks, what is the spatial resolution of the simulations used to conduct the simulations for part 2? most GCMs struggle to simulate the topographic effects and therefore precipitation patterns over California accurately, which seems like it might be important for the mechanisms you describe. So how do you think the topography of California modifies the basic dynamical argument for wettening?
So I think the atmospheric model we've used for this, it was typically 1 degree resolution. And it's true that that's not perfect, but it's probably good enough for the atmospheric signal, because the atmospheric signals tend to be large scale, 1,000 kilometers. So 1 degree might be enough for that. When we are currently running an ocean model to study the ocean part, I haven't showed you anything because that's just something in progress. We're running the ocean at the 1 and 2 kilometer resolution in order to be able to resolve the upwelling dynamics properly. This is it. Thank you very much. Happy to answer additional questions if there are any about both parts.
Yeah.
Thanks for your talk. Really enjoyed it. I'm wondering, during colder climates like the last glacial maximum, the Southwest was also wetter. I think for different reasons, maybe because of displacement of large scale circulation by the ice sheet.
Right.
But I'm wondering how that mechanism might interact with this one, and how those larger scale mechanisms might also interact with this one in a warmer, potentially more equable. I noticed you put like equable question mark for the Pliocene, but some would argue a equable Pliocene climate.
Nice. So yeah, first of all, during the last glacial maximum, so if you go back in time, say to 16,000 years ago, 21,000 years ago, 21,000 years ago is the last glacial maximum where the Laurentide ice sheet that covered North America was at its maximum strength. And as you pointed out, this big mountain of 3 to 4 kilometers of ice, I think, over North America redirected the tropospheric jet southward. And that led to more precipitation over this area that we're talking about. And this area was therefore wetter. Min, the student who did this work at the end of his PhD, when he was finally free to do interesting stuff and didn't have me bothering him, did some really interesting work on that. But this is a very, very different mechanism. It's sort of a topographic effect of the ice moving the atmospheric circulation and so on. I think that paper is coming out soon. So look for Min-Fu. If you go to equable climate, so typically 50 million years ago, the Eocene people think about as equable. We just don't have evidence for now what was the sea surface temperature of California. Then it's just too far in the past to be able to know details that are useful to know. You imagine that something like that might have happened, but it's kind of nice to have the Pliocene only 2 to 5 million years ago, where we know more about the SST, about the land wetness and so on. And so we have actually observational constraints. So that's, I do love the Eocene as a problem, but in this case of this particular problem, the Pliocene provides more data and therefore more interesting motivation, I think.
Another question in the chat. Xiu Zhao asks, how is the MJO forcing applied in the idealized model for part 1? Are there other wave processes similar to MJO influential for the frequency of SSW?
How is the MJO? Tell me again. How
is the MJO forcing applied in the idealized model for part 1?
Okay, yeah. So when we make the MJO stronger, we simply prescribe a 40-day periodic signal because the MJO roughly has a 40-day signal. We impose an artificial 40-day signal in the tropics that emulates a stronger MJO. I'm hoping that answers the question, yeah.
So the positive feedback loop that you described in your first simulation, you imposed a strong area of wetland, which it's with a large uncertainties. And when you close the loop, the surface temperature, you also have a strong uncertainty in there that you don't know where the threshold that will trigger that.
That's right.
And it seems that they have to be coupled.
That's right.
So you're just describing two very extreme situations in order to feed that feedback loop. So in a way, it's only can happen in extreme situation until then it will stay dry, in my opinion.
You might be right. You're absolutely right that we're looking at two different parts of the puzzle. One is we impose a large SST perturbation and we see what the atmospheric effect on wetness. And two, we impose this strong wetness signal and we see what the effect on the winds are. That's true. in an ideal world, you would want to have a model where you could just increase the CO2 and see how all of this is happening. But as I mentioned, these climate models don't resolve the upwelling system, so you can't really do that, unfortunately. But yeah, ideally, that's exactly what you would want to do. And as a result, I would agree with you that we can't tell you when the feedback would be triggered, because we're sort of playing with different pieces rather than with the entire picture. Yeah. So that's why I'm saying this only tells you something about the fact that the uncertainty in this projection is larger than you would think, but I can't claim this to be a projection because of the limitations you just mentioned.
So I have a follow-up to that, exactly. So you've triggered the positive feedback by making the ground surface wetter. Have you also attempted to say trigger it by changing the upwelling? Is there a way to, like, go ahead and make that start with a dry California, but make that
indirectly, yes. Here, this would be the figure that you want to think about. So rather than triggering or stopping the upwelling, we impose a sea surface warming that would be the result of a weaker upwelling. So everything we're doing is in the context of an atmospheric model, atmospheric dynamics. So when we impose such an SST perturbation, this means that we're thinking that the upwelling is weaker, and as a result of that, the SST is warmer.
Okay.
Yes.
So Daniela Tuma asks, for part 2, I wonder if biases in the soil moisture are playing a pretty big part in this feedback loop, not showing up in future simulations. Some models evaporate their soils too quickly and may not allow for a wetter California in a warmer climate, and would break this feedback loop, the feedback loop that you show there.
Yeah, again, even if a model is trying to increase the soil moisture and participate in this feedback, the fact that the upwelling can change because they don't resolve the upwelling properly won't allow them to simulate the full feedback. You wanted to ask something?
So if you're increasing CO2, would it produce like that sort of sea surface temperature perturbation, or would it be more diffuse over, like, say, the whole ocean? And
yeah, this is how we produce this SST perturbation. Let me explain how we derive this SST perturbation. So we look at the present day SST and say this is the 20-degree isotherm, and then it goes south here. So what we're doing is deciding on some longitude and saying, okay, let us set the SST from this longitude eastward to its zonal mean west of that area. So depending on what longitude we use, this is 135, this is 150. So 150 means that we go to all of this area and we set all of the SST from this point all the way to the coast to be equal to the zonal average, because we're saying this cold area here is because of the upwelling. It's not only because of the upwelling, there's also the California current and so on, but never mind. So depending on what longitude we use, we can get either a small SST perturbation or a large one. Studies of the SST today suggest that the upwelling effect extends hundreds of kilometers away from the coast. There's Mike Spall from Woods Hole did a nice paper on this like 5 years ago. So these perturbations are the right scale in terms of the distance from the coast.
Okay, one more. During the motivation, you talked about other upwelling zones, not just California. And Gita brought up sort of there's some geographic particularities to California that make this area maybe different than those other upwelling zones. Have you looked at simulating, like, does this feedback operate in the same way for some of these other regions?
Yeah, so we looked in this paper that I'm describing in this talk, we looked at all 4 regions. There's the California, Humboldt, Benguela, and the Canary Islands. These are the 4 upwelling systems. You can see that the indications are that in this area right here, the warming in the Pliocene wasn't that big. So we try in the paper to explain why this feedback would not work for that one and would work for the others. So we're actually looking at all of them and are trying to explain differences between them. I didn't get into that. It's a long story.
Thank you.
Great. Thanks for asking so many questions. Really fun.
Thank you very much for the